Hi, my name is Karen. Today I'm going to talk about the project that I worked on with Bryan Russell and Justin Salamon from Adobe Research on audiovisual spatial correspondence. Please use wired headphones to experience the spatial audio in this presentation. Otherwise, you can always check out the video later on our project website. I'll start by showing two video clips with spatial audio. In the first video, we see a speaker moving from left to right, in correspondence with a voice moving from left to right. In the second video, we perceive a discrepancy between the video and the audio. The speaker moves from left to right, but the sound moves from right to left. We can perceive the difference between these two videos due to the spatial audio cues. Spatial audio captures the time delays and intensity differences in the sound waves that enter our left and right ears when we listen to real sounds. Humans naturally establish a spatial correspondence between sight and sound, which is why we could tell that the first video is correct and the second video is flipped. We hypothesize that the ability to understand and integrate spatial cues from audio and video can enable machines to interact more seamlessly with the real world, for example, in navigation and interaction with humans. In this work, we ask whether we can teach machines to establish spatial correspondence by leveraging videos with spatial audio. Our first challenge is that there are limited video datasets with spatial audio. As a first contribution, we introduce a new dataset of ASMR videos from YouTube. The YouTube ASMR 300K dataset consists of individuals facing a camera and microphone, moving around and making different sounds. YouTube ASMR 300K is the largest reported video dataset with spatial audio, with over 900 hours of footage, and is accessible from our project website. The second challenge we face is learning audiovisual spatial cues from this data without labels. To address this challenge, we propose a self-supervised pretext task for jointly learning audio and visual spatial cues. We feed the model either videos where the audio channels are unchanged, or videos where the left and right channels have been flipped. The frames go through a visual subnetwork, and the audio goes through an audio subnetwork. The model is trained to determine whether the channels have been flipped or not. We find that the model trained on this task can match human performance on the ASMR dataset. And it does this by establishing spatial correspondence between the audio and visual inputs. On the left here, we show the positions of spatial cues that our model extracts from the audio. And on the right, we show the regions that the visual network learns to attend to. Notice that the learned spatial cues are moving in synchrony. Next, we leverage the learned features to perform downstream tasks that could benefit from spatial understanding. We focused on three tasks: audio-visual face tracking, audio-visual sound source separation, and audio-visual spatialization. The first two tasks are described in our paper. Audio spatialization involves transforming a mono audio track without spatial cues to audio that has spatial cues, using information from the visual input. Since our task teaches a model how the features in the visual input correspond to spatial cues in the audio, we hypothesize that they would be useful for this task. We evaluate the pre-trained visual features using an improved version of the mono to binaural model. We find that our features outperform other self-supervised pre-training methods and also slightly outperform features trained on ImageNet classification. Here's a video that my co-author Justin recorded using a regular microphone. Notice that the mono audio comes from a fixed location.
Now I'm in the middle, now I'm on the left, and now I'm on the right.
Here's the same video that has been upmixed using the model trained on YouTube ASMR. Notice that the sound moves in synchrony with its position on the screen.
Now I'm in the middle, now I'm on the left, and now I'm on the right.
Our final contribution is showing that spatial understanding can be extended to more generic types of video with spatial audio, such as 360-degree videos. Instead of teaching the model to tell left from right, we can teach it to tell front from back by randomly rotating the spatial audio channels. We find that this technique is useful for extracting spatial cues from the audio, and that the features transfer well to sound localization tasks. Please visit our companion site for project materials, including access to our dataset, YouTube ASMR 300K.